So we are discussing about magnetic effect of current, and these are series of classes where we are solving standard 12 CBSE board questions and answers of previous years. Okay, let's begin. Now a small compass needle of magnetic moment m, small m is the magnetic moment given, is free to turn about an axis perpendicular to the direction of uniform magnetic field. Okay, B is the external magnetic field given. The moment of inertia of the needle is given as I. The needle is slightly disturbed from its stable position and then released. Prove that it executes simple harmonic motion and deduce the expression for time period. You have to find out the prove that it is simple harmonic motion. So how to prove simple harmonic motion? Acceleration is proportional to minus displacement, correct? This you have to prove, and you have to find out the time period, correct? And second part of the question says that compass needle free to turn in a vertical plane orient itself with its axis vertical at a certain place on earth. Find the horizontal component of Earth's magnetic field and angle of dip. Okay, so first of all let's visualize this question. So suppose we have a external, this is m is the magnetic moment. So if m is the magnetic moment and 2L is the length, then magnetic moment, m is the pole strength actually. If capital M is the pole strength, small m is magnetic moment. So magnetic moment is equal to how our pole strength is related with magnetic moment. This is pole strength into the length of the magnet equal to the magnetic moment. Okay, this we are clear about it. Now here the needle is is kept in an external magnetic field. Okay, so this is suppose the uniform magnetic field. How uniform magnetic field is presented? We know that uniform magnetic field is represented by equispaced parallel lines. Okay, so if you keep a magnetic needle here, okay, so in its stable position, how this magnetic needle will align? Magnetic needle will align with its axis parallel to the direction of the external magnetic field. This is how the needle will lie. Now if you displace a little, what will happen? Now if you displace a needle, the needle will come, how the needle will behave. So in order to calculate all these things, let's represent this external magnetic field by this, and you have displaced the needle. So this is the axis of the needle. Okay, this is our needle. Okay, let's just represent this needle first. This is how the north pole and south pole of the needle represented. Okay, so you have displaced this needle by an angle theta, say theta. What will happen? This external magnetic field will exert a force on the north pole. So along the direction of the field, it will exert a force like this. If small m is the if capital M is the pole strength, then what is the force? Pole strength into the magnetic field. This much force will be exerted on the north pole, and in the south pole this force will be towards this in opposite direction. So MB force will act in this direction, correct? So now, so these two forces on the north pole and south pole are equal and opposite, parallel. Okay, they will constitute a couple. Because of this couple, this needle will experience a torque, correct, along clockwise direction. In this direction, it will if you displace a little, if you displace by an angle theta, then this torque will try to bring back the needle along the axis. But as it comes to motion, in light needle, it comes to motion, what will happen? It will cross this mean position and it will come somewhere here. So this is again a position which is unstable position. So hence this needle will execute simple harmonic motion. Okay. So let's find out what is the torque. So if MB is the force, MB force here, then torque is equal to force into perpendicular distance. Now this length between the magnetic north and magnetic south, this is the magnetic length is 2L, correct? 2L is the length. Now if we join this force with this, what is the perpendicular distance between this force? This is the force. If this angle, that is the axis of the needle, makes theta angle with external magnetic field, then this angle is theta, correct? So in this triangle, this particular perpendicular, this perpendicular is 2L sin theta. Sin theta is P by H, so 2L sin theta. So what is the force? What is the torque? Torque experienced is equal to force into perpendicular distance. So force is MB and the perpendicular distance is 2L sin theta, correct? So this M into 2L is the magnetic moment which is represented, which is given in this question as a small m, correct? So M into 2L, this two product will give me the magnetic moment into B into sin theta, correct? This is the torque experienced, correct? And this torque is, what is the nature of this torque? This is a restoring torque, because when we are displacing by an angular displacement theta, this, because of this clockwise torque, this needle try to come back to its initial position, correct? So we can represent it by minus with a negative sign, with a negative. What is this negative sign means? Negative sign means restoring in nature, correct? And if theta is very small, then sin theta is nearly equal, sin theta is equal to nearly equal to theta, correct? When theta is small, theta is very small angular displacement, so we can write it like minus m into b into theta. What is theta? Theta is angular displacement. Now in case of linear motion, force is mass into acceleration, correct? In case of angular motion, what is analogy? What is replacement of force? Torque, no? Torque, and torque is equal to moment of inertia into angular acceleration. So this is force is equal to mass into acceleration in linear motion, and in angular motion, in place of force we have torque, in place of mass we have moment of inertia, and in place of linear acceleration we have angular acceleration, which is d2 theta by dt square, correct? In differential symbol we write d2 theta by dt square, correct? So because of restoring nature we can write minus, this is the acceleration, so minus m into b into theta equal to moment of inertia into angular acceleration d2 theta by dt square. Okay, or you can write, because we are not going to solve this differential equation, you can write simply acceleration, correct? So now here acceleration is proportional to the minus of displacement, because m is your magnetic moment, b is the induction vector of the field, I is moment of inertia. These three quantity I, b and m all are constant, so we can write d2 theta by dt square means the acceleration. How acceleration comes? D theta by dt is the angular rate of change of angular velocity, correct? Now if we differentiate this velocity, then it will become d2 theta by dt square, correct? D of d theta, d of dt of d theta by dt is, this is acceleration. So now in this equation we find that the angular action is proportional to minus of angular displacement, correct? Such motion where acceleration is proportional to minus displacement is a simple harmonic motion, correct? So now we have proved that this is a, if we displace a little and then left it, then it will execute to and fro simple harmonic motion, correct? And what is time period of simple harmonic motion? time period of simple harmonic motion in case of angular motion, we have root over 2 pi angular displacement. This we can represent, okay, angular displacement by angular acceleration, correct? So we have d, okay, so d2 theta by d2 theta by dt square will be I by mb. So if we take the magnitude of it, it will be 2 pi root over I by mb, correct? M into b. So this is the time period, correct? So let's see how you can take the screenshot here. So we have represented the needle in this way. mb is the force. This is the induction vector of the external field, and this is the equation of motion. Moment of inertia into angular acceleration is equal to the torque, restoring in nature. Negative sign indicates that restoring nature. So therefore time period of simple harmonic motion. So this actually proves that the motion is simple harmonic motion. Any motion in physics, if you want to prove that it is simple harmonic motion, SHM, then you have to show that force is equal to, that is acceleration and displacement are related with a negative sign, correct? And now time period is root over 2 by angular displacement, angular acceleration in case of rotational motion, and in case of linear motion it is simply displacement by acceleration, correct? So this is I by mb is our time period, 2 pi root over I by mb, correct? Now second question. In the second question it asks that the needle aligned vertically in the horizontal component of Earth's magnetic field, okay? Now say, now we know that Earth is a magnet, correct? Now Earth is a magnet. This is the geographical north, geographical south, geographical north and geographical south. And magnetic north and magnetic south is not at the same point as the geographical north, geographical south. This is our magnetic north, magnetic south, correct? And the needle indicating that north, it is actually north seeking pole. It is not, no, we say north pole, but actually the needle indicates that this is the north seeking pole. And the angle between the geographical north and magnetic north plane is 18 degree about, correct? These two planes are different planes. So a plane drawn through magnetic north, magnetic south is called magnetic meridian plane. Correct? And the angle between these two plane, magnetic north, magnetic south plane and geographical north, geographical south plane, this angle is called angle of variation, okay? This we have studied. So suppose BT is the terrestrial magnetism. Because of terrestrial magnetism, this is the Earth's magnetic induction vector, Earth's magnetic field, correct? BT. Now in this field, the needle is inclined by an angle delta. Delta is what? With the horizontal part of this plane, magnetic meridian plane, the needle makes an angle delta. This delta is called the angle of dip, correct? Now if we divide this Earth's magnetic field into two mutually perpendicular components, then the horizontal component, this is called the horizontal component of Earth's magnetic field, which will be how much? BT cos delta, BT cos delta, correct? And this is cos, this is also vertical component is also BT into cos of angle between BT and the vertical part, correct? BV is the vertical component, is equal to BT cos, this angle is 90 minus delta, so this is equal to BT sin delta, correct? Sorry, sin delta. So these are the two components of Earth's magnetic field. Horizontal component is BT cos delta and vertical component is BT sin delta, correct? And if we divide this BT sin delta by BT cos delta, then what we will get? We will get BV BT sin delta by BT cos delta equal to BV, means vertical component of Earth's magnetic field, by BH, horizontal component of Earth's magnetic field, correct? So sin delta by cos delta is tan delta, correct? So tan delta equal to BV by BH. Also, in this, from law of parallelogram vector, we can show that BV square plus BH square is equal to BT square, correct? Or if we square and add these two, then how much? BT square sin square delta plus BT square cos square delta. So BT square common, sin square delta plus cos square delta is 1, equal to squaring and adding. Huh? So it is BV square plus BH square, correct? So this is how the vertical horizontal component is related with the magnetic induction vector BT, correct? Now, next question. Circular coil of n turns, radius r, carries current I. Okay, so n is the number of turn, I is the current in that coil, and A is the area of the coil. Okay, now it is unwound and rewound to make another coil of radius r by 2. Okay, so the entire coil is first of all stressed, okay, and then it is rewound in such a way that now the radius is r by 2. Initial radius was r, now the radius is r by 2. Now the current remaining the same, calculate the ratio of magnetic moments of new coil and the original coil. The new coil will have different number of turns because now the size of this coil is reduced by r by 2. Okay, original number of turns is n, correct? So suppose m dash be the magnetic moment when the radius is r by 2, correct? So length of the wire in the initial position when the radius was, when there was n number of turns and radius was r, okay, this is n number of turns. Now if radius is reduced by r by 2, okay, now it is smaller, number of turn will change. Suppose n dash is the number of turn, radius is r by 2, but the length of the wire is same, correct? So length is equal to L dash. Okay, L dash is the length when radius is r by 2, correct? So total length of the wire is equal to 2 pi r into number of turns. One length of one turn is equal to 2 pi r, length of n number of turn is 2 pi r n, correct? Equal to the total length of the wire when it is reduced, when the radius is reduced by r by 2, it is 2 pi r dash into n dash, correct? So in this way we find that r dash is, but it is given that the new radius is half of the original radius. Now if we put the new radius as half of the original radius r by 2, then we find that now the number of turn will be twice the original number of turn, correct? So we know that a coil where we have a current passing, correct, serves as a magnet, correct? So what is the magnetic moment of this coil? I into a current into the area of the coil, correct? So now this coil, okay, so if there are n number of turn, that is Ia is the magnetic moment. If for one turn, if n number of turns are there, then total magnetic moment will be Ian. So initial magnetic moment is this, and now when its radius is r by 2, this number of turn is changed, it has become 2n, correct? So this is what is done here. Magnetic moment is equal to n dash I into a dash. A dash is the area when the radius is r by 2. So a dash is equal to pi r by 2 whole square, and n dash is equal to twice of n, correct? So this is the magnetic moment. So now we find that it is n I r square by 2, but okay, and there will be 1 pi, correct? One of the two goes here, so it is n into I into pi r square by 2. Sorry, 1 pi is missing here, pi r square by 2. Okay, So but Ni into pi r square is the initial magnetic moment of the coil, correct? So therefore we find that m dash by m equal to 1 by 2. Okay, so the magnetic moment, okay, after reducing the radius by r by 2 to the original magnetic moment when the radius was r, in the ratio 1:2, correct? Tricky question. Only you have to find out the number of turns increased by twice, correct? Next question. Write the expression for F acting on a charged particle of charge Q moving with a velocity v in the presence of both electric and magnetic field. So a charged particle is moving in a combined electric and magnetic field. Okay, so you have to find the expression for force. How much force will act? Okay, now obtain the condition under which the particle moves without deflection through the fields. Okay, this is a 5 marks question. So you know that when a charge is in motion, so it interacts with the magnetic field. So when the charge is at rest, it only experiences electrostatic force, which is Q charge into the electric intensity, correct? This is the electric force acting on the Q charge. But when charge is in magnetic field and the charge is moving, then it experiences a force Q into the velocity of the charged particle into the induction vector of the external magnetic field. This is the force this is the magnetic force experienced by this moving charge, correct? So we have to add both the forces because this charged particle is in the external magnetic field B and moving with a velocity v will experience both the forces. Because of the charge it will experience electric force, because of its motion it will interact with the external magnetic field and it will experience a magnetic force. So these two forces is, we can take Q common, E plus V cross B. Okay, so this you have to deduce the expression for force experienced. This is simple. Now for null deflection, the force due to the electric field must balance because of the force due to the magnetic field. So this should be there, correct? And this is the velocity and induction vector cross product. It is at 90 degree, so VB into sine 90 degree. A cross B is AB sine theta. So angle between the velocity and induction vector is equal to how much? This is 90 degree. So Q cancel out. We have expanded this cross product as VB is sine 90 degree. So therefore the velocity is equal to the electric field divided by the magnetic field. The ratio of electric field to magnetic field, electric intensity to magnetic intensity is the velocity. So this is how velocity is related. So velocity should be the ratio of magnitude of electric field to the magnitude of magnetic field, correct? Now here it asks that a rectangular loop L into B carrying a steady current I placed in a uniform magnetic field B. Prove that the torque acting on the loop is given by M cross B, or M is the magnetic moment of the loop. This is actually we have already discussed this. This is principle and theory of moving coil galvanometer. So how much force is experienced by a rectangular torque in an external magnetic field? This already we have discussed, correct? So you can take the screenshot. Earlier we solved this question, so we will skip this one. Okay, so torque is equal to M cross B. Now next question. Explain, giving reason, the basic difference in converting galvanometer into a voltmeter and ammeter. Okay. So what a voltmeter does, a voltmeter actually measures the potential difference. To convert a galvanometer to voltmeter, so what is the purpose of voltmeter? So we need to connect this voltmeter with a high resistance in series. High resistance in series. This is how galvanometer is converted to voltmeter, correct? So that if more potential is applied, in order to protect it, high resistance is placed in series. So some of the potential drop will happen across the galvanometer, remaining potential drop will happen across this high resistance. So a high resistance in series connected with the galvanometer coil converts it to a voltmeter. Whereas if we want to convert a galvanometer to ammeter, then we have to protect it from high current. So whenever the high current is coming, so we have to give a bypass route to this current. So to give a bypass route, we connect a low resistance in parallel. This low resistance in parallel, we call it shunt, correct? So a galvanometer is converted to ammeter when a low resistance is connected in parallel. So main current, only a part of current, that is, will pass through the galvanometer. Remaining current, that is main current minus the current passing through the galvanometer, will pass through this ammeter. So a low resistance in parallel converts a galvanometer to ammeter, correct? Okay. So in case of ammeter conversion, the potential drop across this galvanometer is how much? You show galvanometer resistance separately as G, then parallel connection of this galvanometer with a low resistance, this is shunt connection. Okay, so in the given question we have to find out what is the shunt resistance. So this is okay. Okay. Now, expression for resistance of the, okay, so this is actually the figure for converting galvanometer to ammeter. So galvanometer to voltmeter conversion is what? This, correct? Okay. So in case of ammeter, this galvanometer resistance and shunt resistance both are parallel. So what is the effective resistance? R is the equivalent resistance, GS by G plus S, correct? In case of voltmeter conversion, so potential drop across the galvanometer is equal to main current into G, correct? Plus potential drop across the high resistance is equal to main current into resistance. So if V is the potential applied across this, then some of the potential drop will happen across the galvanometer, which is main current into galvanometer resistance. The other will happen through this, correct? Main current into the high resistance, correct? So this is how we can convert it into a voltmeter. Now, next question. Two long straight parallel conductors carrying steady current I1, I2 separated by a small distance. Briefly explain with the help of suitable diagram how the magnetic field due to one conductor acts on the other, hence deduce the expression for force between the two conductors. Okay, so we have already discussed. Only for your information, suppose if the two currents are flowing in opposite direction, I1 and I2, okay, then what will happen? They will repel each other. Okay, they will repel each other. When the currents are flowing in the same direction, they will experience attractive force. This already we have discussed. Anyway, this answered here, correct? You can find out the force due to force on the second wire, force on the first wire, correct? And it is using the Fleming's left hand rule, you can find out the direction. So this is already discussed. Okay. With the label diagram, studying principle of cyclotron. Cyclotron we have already discussed. Explain briefly how it works. Okay, so that the cyclotron frequency, okay, is independent of energy of the particle. So we will calculate this cyclotron frequency. Is there any upper limit on the energy acquired by the particle? Give reason. Okay. So this part is new for us. We'll explain this. Now, when the charged particle moves between the D's, there in cyclotron we have two D's, correct, D1 and D2, and when it jumps from one D to other D, it experiences acceleration. As a result, its radius increases. So that is why the charged particle executes a spiraling motion, and ultimately it comes out through the cyclotron with a very high energy, with a very high speed. Okay, so what is the physics behind it? Okay, the physics is the centripetal force required to move in the circular motion is provided by this magnetic force. Okay, Q into V cross B means QVB, correct? So this is how we can find out the velocity of the particle, which is equal to this. Now the period of revolution is equal to 2 pi r. Suppose at any instant the radius is r. So what is the time period? What is the time taken to rotate in 2 pi r? 2 pi r is the total length of the boundary divided by velocity is the time period. So it is 2 pi r, and velocity is equal to, we know that QB r by m. So this is QB, okay, r by m. So one of the r cancel out. So it is 2 pi m by QB. Now what is frequency? It is reciprocal of time period, 1 by t, correct? So if t is equal to 2 pi m by qb, then frequency is equal to q. Just reverse it, numerator becomes denominator, correct? qb by 2 pi m. So here the frequency of revolution is independent of energy of the particle. There is nothing called velocity here, correct? No velocity in this expression. So that is, it is independent of energy. There is an upper limit of energy acquired by the charged particle. The speed, hence the energy gain is maximum at upper limit. When the radius of the moving path is equal to the radius of the D's. D's means this D's. Okay. So the velocity is constrained by the construction of cyclotron, where the radius is the constant, radius of the D's, correct? So this part is answered. Now level diagram explains principle of working moving coil galvanometer. We have already explained. Why, while using moving coil galvanometer as a voltmeter, a high resistance in series is required, whereas an ammeter shunt is used. That we have explained. High resistance in series means it protects from high voltage, correct? Low resistance in parallel means it protects from high current, correct? So this, in the previous question we have explained it. Anyway, you can take the screenshot of it. Okay, so this is complete working of moving coil galvanometer. We have also a lecture for moving coil galvanometer, okay? So you can follow that. Okay. So this is already explained. Derive expression for force between two parallel wires. This already we have explained. This is also a repeat question. Check the screenshot if you need. Now, okay, this question. Define current sensitivity. Okay, define current sensitivity and voltage sensitivity of a galvanometer. Increasing the current sensitivity may not necessarily increase the voltage sensitivity of a galvanometer. Justify it. Okay. So what is current sensitivity? It is defined as the deflection produced in the galvanometer on passing unit current through the coil. If very less amount of current can deflect the galvanometer coil, it means that it is more sensitive, correct? So it is defined as the deflection produced by galvanometer on passing current. So this is how the current sensitivity is defined. What is voltage sensitivity? It is defined as the deflection produced by the galvanometer when a unit voltage is applied across the coil, correct? So if alpha is the deflection produced on applying voltage V, then voltage sensitivity is defined by the deflection produced divided by the voltage applied, correct? So from this we can find out that it is N B into A by K into R. The voltage sensitivity may be increased by passing how to N is the number of turns, B is the induction vector, A is the area, K is the constant of the galvanometer, R is the radius, correct? So if we want to increase the voltage sensitivity, you have to increase the numerator. Any of the parameter in the numerator, if you increase the voltage sensitivity, will increase, correct? So NBA, if you want to increase, then either you have to increase number of turns, magnetic induction vector or area. Okay. Or you can increase the voltage sensitivity by reducing the denominator. In the denominator we have K and R. So by decreasing K and R, we can increase the voltage sensitivity. Now, in case of current sensitivity, if we want to increase NBA, can be increased, okay, by increasing NBA or decreasing K. So hence, increasing current sensitivity may not necessarily increase the voltage sensitivity of a galvanometer, correct? Because see here, in case of current sensitivity, there is nothing called R, correct? So these two are different things. One is sensitive towards current, other is sensitive towards voltage. Now this is Faraday's laws of electromagnetic induction. So what is Faraday's law? Faraday actually tried to find out what is the impact of whether when a magnet is in motion, okay, or when current flows, then we know that there is a magnetic field produced, but can a moving magnet, okay, or can a variable magnetic field produce current? That was all about Faraday's experiment. So he proved that there are two laws. One is the induced EMF is proportional to the number of turn, and the other is induced EMF is proportional to the rate of change of flux, okay. So d phi by dt, correct? So a jet plane, second part of this question, a jet plane is traveling towards west at a speed of this. What is the voltage difference developed between the ends of the wings having span of 25 meter width, okay? If Earth's magnetic field is given as 5 into 10 to the power minus 4 Tesla, and angle of dV is given as 30 degree. So whenever magnetic flux linked with the circuit changes, induced EMF is produced. Means in order to produce electromagnetic induction, okay, we need a flux, magnetic flux, and it should change with time. No, it should change with time. Okay, either you have to move the magnet towards a static coil, okay, then as long as it will move, the magnetic flux cutting the coil will change. Or you can produce instead of magnet, you can produce a magnetic field, okay, by passing a variable current here, okay, this by keeping another coil here, and this, if we continuously change this current in this coil, then the magnetic flux will also change. Now these varying lines of force when cut the plane of the second coil, then here also current EMF will be induced as well. When the EMF is induced, then the current flows through this circuit. So this is all about our Faraday's laws of induction, and induced EMF lasts as long as the change in, okay, so for continuous motion we need that the flux should change continuously. If the motion of this magnet stops, or if we pass DC current here, then there will not be any varying magnetic lines of force, varying magnetic flux, then EMF will not be induced, correct? So it must cut the plane of the coil, it must change with time. The magnitude of the induced EMF is directly proportional to the rate of change of magnetic flux, okay, and number of turn, of course. So this is E induced EMF is equal to proportion of minus N d phi by dt. This minus sign indicates that as per that EMF induced, okay, is in the reverse direction. Okay, so Lenz later explained, we have Lenz's law, what will be the direction of EMF produced. Now come to the second numerical part of it. Here the velocity is given at 1800 kilometer per hour. So we know that if you want to convert kilometer per hour to meter per second, you have to multiply it by 5 by 18. Or kilometer to meter is 1000, hour to second is 60, correct? So it is 500 meter per second. So first of all, we have converted the unit of measure to SI unit. Okay, delta is angle of dip, H is the horizontal components of Earth magnetic field. Now we have just in the last question we have proved that BV vertical component by BH, okay, is equal to tan delta, where delta is the angle of dip. So here instead of BV, BH, we have represented V and H. Correct. So this is the relationship we have. So therefore vertical component of Earth's magnetic field is equal to horizontal component into tan of angle of dip, tan 30 degree. So this is how much? It is Tesla, because it is the vertical it is magnetic field, the unit will be in Tesla. Correct. Now next question. This is why should the material used for making permanent magnets having high corrosivity? Okay. So for permanent magnet we want that high corrosivity means what? It can withstand high external magnetic field and electric field. Okay. Therefore high corrosive means magnetization is not destroyed by stray magnetic fields or temperature variation, correct? For making permanent magnet, this property is required, because what is retentivity means after removal of the external magnetic field, it should remain magnet. For a permanent, when we develop a permanent magnet, what is our main objective? That it develops high intensity of magnetization. What is intensity of magnetization? When we put a, suppose this is an external magnetic field, correct? And a bar is kept, iron bar is kept. Now after removal of this external magnetic field, if it retains some magnetization, this bar specimen copy, this bar magnet, then we say that the magnetization developed is more, correct? So corrosive, high corrosivity means it will not, means that it can withstand high external magnetic and electric field. It is required, okay? And high corrosivity means magnetization is not destroyed by stray magnetic fields or temperature. For permanent magnet making, these two properties must, correct? So there are three types of materials, dia, para, ferro. The ferro is ferromagnetic materials like iron materials are used because they have the high corrosivity for permanent magnet, correct? Okay. Now, state Biot-Savart law, use it to derive expression for the magnetic field at the center of the coil. Okay, so we have a coil, it has many turns actually. The coil has many turns. Okay. So for one turn, what is the magnetic field we will calculate, then we will multiply it by N. Okay. And I is the current flowing. So we know that because of this current flowing in this coil, magnetic field is developed. Okay, so for one element, suppose we have taken an element on the circumference here, correct? DL is the element. For element, now let us put a orthogonal system of axis, so that, because ultimately we have to find out magnetic field, and the magnetic field is a vector quantity, it has direction also. So we have to find the direction, we need axis, correct? So x-axis, y-axis and z-axis, these three axes we have taken, one element is taken. Now using the, what is Biot-Savart law? Because of current element of length dl, what is the magnetic field it gives? Okay, it is equal to how much? I into dl cross r. Dl is the length of this element, r cross r by r cube. Okay, r is this direction. So suppose what is Biot-Savart law? Let us understand. Suppose this is current element, dl is the length, I is the current flowing. Okay, so if this is any external point, say P, and this angle is theta, okay, so here how much magnetic field will be produced here, dB, because of this current element dl, where I current is passing is dB is proportional to dB, the magnetic field is proportional to I, dB is proportional to the current element length dl, dB is proportional to the sine of angle between the current element and the axis, means where the direction of this external point, this r vector, correct, unit vector along this direction, so sine theta, and dB is inversely proportional to the square of distance r square. If r is this distance, then as we go further away, the magnetic field reduces by inverse square. So by combining all these things, we find that dB is proportional to ideal sine theta by r square, and then so dB, we find that dB is proportional to I dl sine theta by r square. Now to replace this proportionality sign, we replace it by some constant which is equal to mu0 by 4 pi, correct, I dl sine theta by r square. Now to write r square, we can write r square as r square into r, so, okay, and then this vector r, this is represented in vector form, is a vector representing this direction, correct. So now this r and dl is current element because dB is magnetic field, so this is the scalar equation, so we can convert this equation to vector equation, okay. So r cross dl, so dl cross r will represent dl r sine theta, so these three will represent dl cross r, correct. So this r is taken extra, that is why the denominator becomes r cube, okay. So dB is equal to this, so where theta is the angle between this. So this is how Barrett-Savart law is stated. The magnetic field at the center of the coil we have calculated. So because of this current element, how much? Just apply this. But now say dB equal to, I can represent dB in two ways. One is mu0 by 4 pi I into dl cross r. R is not the unit vector, by r square or r cube, or I can represent this by mu0 by 4 pi I into dl. This r is not the this is unit vector r. Unit vector means magnitude 1, then we need not multiply r by r, denominator numerator, so the denominator remains r square because this is unit vector taken. So this formula we have used, correct. So it is mu0 by 4 pi r square. So because of, so a equal to radius of this coil. Now let us put okay. So this becomes I into dl into angle between dl and the radius vector. Dl is the along the length. If I is the current flowing, then dl is this, and this is the angle between dl and the r, correct, 90 degree. So it is mu0 by 4 pi I by a square. A square is the distance of current element from the point where the magnetic field to be found. This distance is the radius, correct. So this is the distance. So we have taken this as a square. The r is replaced by r square is replaced by a square. dl into 1 is the unit vector taken, sine 90. It is mu0 by 4 pi I dl by a square. Okay, now that was because of this single infinitely small length current element. We have find out what is the, because of dl we find out what is the dB, correct. Now in order to find out the magnetic field at the center, because of the entire wire having n number of turn, for the entire wire we have to integrate this expression mu0 by 4 pi I dl a square, integrate it, correct, and for all the turns we have to multiply it by number of turn, correct. So when we integrate, that is integration of dB will give us the total magnetic field produced because of all the turns, because of this entire circumference of this coil, correct. So dB, if we integrate, that is mu0 by 4 pi I dl by a square. Now here a is the radius, I is the current, mu0 by 4 pi is permeability and constant. All these things are constant, we cannot integrate we do not have anything, only variable part is dl. So what is dl? Dl is the total length of this element. Okay, so for one turn the length is 2 pi into a. This is the perimeter of this circular turn, and we have n number of turn. This is the total length. So integration of dl means n into 2 pi a, correct? So we have put this value here. It is mu0 by 2 ni by a. So remember, this is used in numerical also, that a current carrying loop behaves like a small magnet having north-south pole, and what is the magnetic field at the center? It is mu0 by 2 ni by a. Correct? This is the magnetic field produced. Okay, so draw the label diagram of moving coil. Acha, if you want to represent the flux, okay. Now, suppose current is flowing like this. So remember, the north pole will be developed like this along this direction. In this direction, north pole will be produced, and this will be the. This is from the north pole. We know that the magnetic lines comes. So this is, and in the south pole it terminates. So direction will be inward. So today is the first day of this 2025. So it's happy new year for all of you, and we are actually, see, already crackers are bursting here. So wish you all a very good beginning, and your examination for those candidates who are appearing for CBSE Std-12 is just in the February. Just exams dates are also declared. So I wish all of you to have a very hard work for this exam. Be sincere about this, and I wish all of you to have a very good examination. So today we are actually finishing the magnetic effect of current and magnetism. Okay, so bear with this cracker sound, because now it's morning 5:33 a.m. So people are still enjoying Happy New Year in Mumbai. So let's continue our discussion with this. So we have a moving coil galvanometer, state principle on which it works. Already we have discussed. Mathematical expression for force per unit length experienced by each of the two long current carrying conductors placed in parallel. This also we have explained, correct? Repeat question. With the help of label diagram, explain principle working of a moving coil galvanometer. This also already we have explained. Biot-Savart law. Okay, just check it out. So okay, this is something interesting. State Biot-Savart law. Using the law, derive the expression for magnetic field due to a current carrying circular loop. That also already we have discussed. Now two small identical circular loops marked 1 and 2 carrying equal currents are placed with their geometrical axis perpendicular to each other. Means one coil is kept like this, so its geometrical axis is this. Another coil is kept in a horizontal plane like this, so that its axis is like this, correct? Okay, this axis is this, correct? So the magnetic field produced because of the first coil is like this, okay, B, and suppose this magnetic field produced because of the second coil is perpendicular to this. Suppose this magnetic field is B dash. Okay, this is how it is represented each other. So find the magnitude and direction of the net magnetic field. Okay, so these two magnetic fields are at right angle, correct? So what is the direction and what is the magnitude? So we have to use law of parallelogram of vector. So first of all, Biot-Savart law is explained. Now this part, two magnetic fields at right angle, correct? So okay, so this is mu0 by 2 pi I dl by r cube. So magnetic field due to all such current elements will point in the plane of the paper. Okay. Now magnetic field at, okay, here magnetic field is at the, on the B1 is the magnetic field produced because of the first coil, correct? This is the first coil. So this produce, suppose north is produced here. Na? If we rotate along the direction of current, if we rotate our right hand along the direction of current, the thumb gives the direction of magnetic field, correct? So this is B1. But this B1 is at a point at certain distance, not at the center. Earlier we found magnetic field at the center of the coil. This is at a distance x from the center of the coil. So we have derived this expression already. It is mu0 I r square by 2 x square r square to the power 3 by 2. Similarly, magnetic field produced because of the second coil. This is suppose second coil. This magnetic field is B2. Okay. So this distance is how much? This is also at a distance x. Correct. So these two magnetic fields B1 and B2, B1 and B2 are two orthogonal magnetic fields, two mutually perpendicular magnetic fields, correct? So that the resultant magnetic field can be obtained by using the law of parallelogram vectors. Because it is at right angle, it is simply B1 square plus B2 square plus 2B1 B2 into cos 90. Cos 90 is 0, so we are not writing the B1 B2 cos B1 B2 to B1 B2 cos 90. So this part is 0. So it is simply the resultant magnetic field is equal to B1 square plus B2 square root over, correct? This. So both the magnitudes are same because both this point is equidistant from the center of this first coil as well as the center of the second coil, correct? B2, that is magnitude of B1, that is magnetic field because of the first coil, this coil, equal to the magnitude of magnetic field because of the second coil, this, let it be B1, correct? So we have this magnetic field, this is B1, this is also B1 in magnitude, and they are at right angle. So therefore the resultant magnetic field can be obtained by law of parallelogram of vectors, correct? So this gives the resultant. So if resultant is B, then B is equal to root over B1 square plus B1 square plus 2 B1 into B1 cos 90 degree. So this part is 0. Therefore it is equal to 2B1 square. So it is root 2 into B1. So and this angle is how much? 45 degree because both are having same magnitude. So now this is how much? The magnitude of the resultant magnetic field at this point at the cross section will be root over 2 B1. B1 is how much? This is B1. Mu0 by mu0 permeability by 2 IR square, correct? This is IR square and this is x square plus r square to the power 3 by 2. And what will be the direction? Because resultant magnetic field is a vector quantity, so we derive the magnitude. Okay, what will be the direction? Suppose it makes an angle theta. Okay, so then what is this direction? Suppose this is OE. What is the direction of the resultant magnetic field B? So tan theta is given by P by B, B1 by B1. Both the magnitude this and this are same. So it is 45 degree, correct? Tan theta is equal to 1. So theta is 45 degree. So it will make this resultant magnetic field here will make 45 degree with either of the axes, with this or with this, correct? So this gives the resultant of this thing. Okay, so next we'll discuss about we'll discuss also 2024 and last 5 years questions of magnetic effects of current. But before this, let us finish first whatever we have, like all the chapters. Electromagnetic induction will be our topic for the next class, and alternating current. Okay, thank you very much.